Okay, this is my solution for the problem we did about pressure in a liquid. And we were talking about a swimming pool, maybe the rec center swimming pool. And we said that it varies in depth, maybe 3 feet. At one end, we can call that about 1 meter. And maybe at the deep end, 6 feet, or roughly 2 meters. Okay, so first we need to talk about why the pressure is different in the shallow end versus the deep end. Okay, so let's see. So what I do is I imagine a chunk of water. A chunk of water at some depth y into the liquid. And it has a, here I'll redraw it over here, and this is a slab, but it's a thin slab, has some thickness dy, and it has an area A. And now I realize that there's pressure pushing in from the rest of the fluid at all points here. But I also realize that in order to balance out the force of gravity, so I'll draw a free body diagram here, in order to balance out the force of gravity, there must be a net force of the pressure upward. So what does that mean? Well, what it means is that whatever pressure there is at the top, let's call it P, there has to be a bigger pressure, P plus delta P, on the bottom. So that when I sum these two vectors together, there's a net force upward that's just the delta P, and since pressure is force per unit area, times the area of my slab. So what we're doing here is we're deriving the equation for hydrostatic equilibrium. Okay, and so if we just simply apply F equals ma to this slab, we get that the sum of the forces on the slab is equal to the force of, not the force of pressure, but the extra little bit of pressure on the bottom times the area, that's upward, minus the mass of the slab times g downward, and the equilibrium part is right here, where we say this is 0. The slab's not accelerating downward or accelerating upward. So how do we make these two terms, have anything in common so that we can continue? Well, what we're going to do is represent the mass of the slab as the density of the fluid times the volume of the slab. Okay, well, the volume of the slab then is just the area of the top times dy, that little differential thickness of the slab. Okay, so when I do that, I get that the pressure differential times the area minus rho times the area dy, oop, I forgot the g, times g, there we go, is equal to 0. And now I realize that for a differential slab, this thing becomes just a differential increase in pressure. The areas also cancel, and so what I'm left with is dp is equal to rho g dy. Great. Now this is a differential equation, and I'll just differentiate each side, integrate each side, and we can write this as that the change in the pressure is equal to rho g times the change in the depth. Here's what I want you to see, though. What I want you to see is that we have assumed, by simply pulling out the rho and the g, well, assuming that g doesn't depend on y is a pretty darn good assumption, although certainly if we were talking about, say, the whole atmosphere, even that might not be a good assumption. But more importantly, what we're assuming is that the density is not depth dependent. And for water, that's a really good approximation. But if we were to do this for, say, air, I just want you to note that that's not as good. an approximation. So I'll write this in the way that we usually write it. We let the pressure be equal to P naught at y equals 0, and then what you have is that the pressure is equal to P naught plus rho g y. Okay, so when we plug in numbers for this, we get the pressure at the top, which is 1 atmosphere, also known as 101 kilopascals, or 10 to the 5 pascals, plus the density of water, 1,000 kilograms per meter cubed, times G times Y. And so we get that the pressure is 10 to the 5 pascals plus 1,000 kilograms per meter cubed times 10 meters per second squared times 1 meter. So let's see, that's 10 to the 3, 1, 2, 3, and then 10 to the 4. So we get, so let's see, 10 to the 5 plus 10 to the 4, that's 11 times 10 to the 4. So that's about 111 kilopascals. And that's the answer. What about the deeper depth? Well, we just add another 10 kilopascals, and so it would be 121 kilopascals. And that's the end. What you want to remember, though, is this more general expression, not necessarily the pressure at the bottom of the rec center pool. Okay, that's it.